Good morning, everyone. My name is Kinman. Today, I'm glad to be here to present our work, mTuner, Accelerating Parameter Efficient Fine-Tuning with Elastic Tensor. This work is done by Kezhao and other colleagues from Pacman Group in Tsinghua University. Here is a quick overview of today's presentation. First, I will start with the motivation, focusing on the challenge in fine-tuned large language models, especially in the context of parameters, efficient fine-tuning. Next, I will introduce our proposed system, mTuner, which is built around a key observation we call Elastic Tensor. And after that, this is the evaluation part and some discussion. First, fine-tuning allows people to adapt a pre-trained LLM to specific domain like medical QA or personal assistance. This adaptation is not only faster than pre-training from scratch, but also much more efficient, since it leverages the general knowledge already captured in the base model. As a result, we can quickly specialize a model without incurring the massive compute and data costs of large-scale pre-training. However, efficiently fine-tuned large model is far from trivial. One key point is that the parameter size during fine-tuning is the same as pre-training, which means that huge memory requirement. But unlike pre-train, fine-tune is often done with limited resource, which means that fewer GPUs and much lower communication bandwidth. As a result, we run into two major issues. The first is many setups simply can't fit this large model into a GPU. And the second, even when we do manage to run them, performance is often bottlenecked by memory swapping or other like inter-GPU connection, which means leading to poor efficiency. Now, let's take a look at parameter efficient fine-tuning, or called PEFT, which has become the go-to strategy for adapting large language model efficiently. We compare PEFT with inference and pre-training. First, during inference, all model parameters are frozen, and we simply perform a forward pass. There's no need for gradient computation or rate update here. And in contrast, pre-training update all model parameters, which is both memory and compute intensive and only feasible in large-scale setup. And for PEFT, instead of update the entire model, it inserts more trainable module like LoRa or adaptation into the model. This module contains a tiny fraction of the total parameters, and this dramatically reduces the memory requirement and reduce the communication overhead of training, while still allow efficient adaptation. With this basic idea of PEFT, let's look at why memory is still a critical bottleneck. Memory plays a key role in enabling training efficiency, and is about both rates and iteration. The first is about rates. If we have enough memory to keep rates resident in GPU, we can reuse them across forward pass or backward passes without consistent reloading or communication them across devices. This enables better parallelization strategy. And on the iteration side, more memory means that we can store intermediate iteration, avoiding expensive recomputation during backward processes. It also allows for large band size, which improve throughput and reduce communication overhead per sample. In short, memory is the enabler of fast and efficient PEFT. There are some key observations that motivate our work. The first is that memory usage during fine-tuning is highly inefficient over time. As shown in this figure, memory spike during forward and backward passes and then drop, a clear peak and valley pattern. The problem lies here is that short-life tensor like activation and gradient compete with long-life rate during peaks, which may cause out-of-memory risk. Moreover, during valid, much of the GPU memory sits idle. This mismatch leading to memory inefficiency, either too much pressure at the peak or raise memory in the between. So our goal here is to find a way to better balance the memory over time. In addition to memory inefficiency, we also observe underutilization of communication, particularly in tensor parallelized setup. Normally, communication will wait until data is ready. For example, when a tensor has been fully computed. This leads to idle time where the legwork bandwidth is not used at all, even though communication could have overlap opportunity. So in this figure, there are key gaps where we could be transferred data. The root cause here is strict data dependence. By relax them, we can start communication earlier and better overlap with the computation. This shows that we need tight coordination between memory and computation. And the third is how data, especially accuracy, are accumulated during training. Currently, every layer uses the same fixed strategy to accumulate accuracy data throughout the forward and backward paths. But as we saw earlier, the memory characteristics during peak and valid period are quite different. Despite this difference, the current approach regularly holds on to memory in the same way across all layers and all phases. This inflexible usage causes inefficient memory utilization, limit our ability to smooth out peak or leverage valid. So these are potential to adapt how we accumulate and release data dynamically, depend on the runtime memory stage. Building on previous point, the important opportunity have introduced flexible into memory management. Since accuracy are generate and saved irregular, while weight parameter can be cached and reused flexible. We can decouple rapidly memory pattern and by adaptive how tensor use memory over time, so that we can balance the life of activation and rate. This flexible memory management is key to improve efficiency, reducing communication overhead, and enable large band size or models. Therefore, our system, mTuner, is designed to release this flexible through the concept of Elastic Tensor. To address the memory challenge we have discussed, we propose a new memory abstraction called Elastic Tensor. Such abstraction provides a flexible framework for dynamic tensor scheduling during training. We define four key operations. First is gather preload tensor earlier for overlap communication. Discuss release memory as soon as tensors are no longer lit. Execute one computation with adaptive memory panning. Checkpoint enable recomputation trade-offs. This operation can perform with arbitrary ratio given fine-grained control over memory and communication. By using Elastic Tensor, we unlock key optimization to trigger the inefficiencies which were mentioned before. First, we use frozen rate inefficiently, avoiding redundant reload and reduce memory waste. Second, we break strict data dependence by allocating and communicating rate earlier, allow better overlap between communication and computation. Finally, instead of accumulating memory uniform, we adaptive manage activation based on real-time management processes. Together, this optimization boosts memory efficiency and throughput, making large-scale path model practical. Let me explain how potential memory adjustment work in package, particularly under FSDP training. In FSDP, before an operation run, is associated with a gather from shot into GPU memory to perform computation. The key insight is that once these rates are gathered, they can be cached locally without any additional overhead. This caching allows us to reuse the rate flexible across multi-operation, reducing redundant communication. By adjusting when we gather and discard this rate, we can efficiently smooth out memory usage and improve training efficiency. mTuner manages memory with 4 distant memory stages during the fine-tuning step. Each stage corresponds to different memory ratio allocated to tensor. and we dynamically adjust this based on the runtime demand. Next, let's look at how we improve communication efficiency by dependence-relaxed communication. As we discussed earlier, training communication pattern which results due to data dependence. This create an idle network time here as illustrated in the figure. Our approach is to shift the communication focus from activation to wait. By insert communication earlier from wait, we reduce communication overhead of the activation, leading a short period from non-overlappable communication. This big stack dependence enable more efficient usage of communication bandwidth. Next, here we highlight how adaptive data accumulation help improve memory efficiency during training. By flexible adjusting the band size across layer, we can control how much activation data is accumulated at once. This strategy allows us to reduce the height of peak memory usage, efficiently smoothing out spike that could cause out-of-memory error. This figure illustrates how dynamically tuning accumulate impacts the backward pass memory usage. To fully leverage Elastic Tensor, we design a schedule search algorithm that automatically finds the best path for training. The goal is meet memory constraint with least execution time. We model that as a dynamic program problem, considering two constraints: peak memory usage, mostly from activation, and valid memory usage, mostly from waits. At each layer, the algorithm explores different implementations of Elastic Tensor operation, like when together, whether to discuss, or something like that. This leads mTuner dynamically tailor the ratio of Elastic Tensor operation based on both compute and memory conditional. Let's now move on to the evaluation part of mTuner. We test our system on a range of model scale, specifically llama model with different size parameters to ensure our technique generalized across different sizes. For hardware, we use both PCIe and NVLink-based GPU servers, cover different levels of interconnection. In terms of baseline, we compare mTuner against different systems like FSDP, DSpeak, Megatron, and Flux. Here are the overall performance results of mTuner compared to existing system. The first figure shows results on PCIe servers, which has relatively lower communication bandwidth. In this setting, mTuner achieved up to 51.2% speed up, with an average improvement of 28.3% speed up. For NVLink servers, the speed up is about 24 at most. On the left, we show result of how ratio of wait data to the total communication affects the effective algorithm bandwidth. This effect is especially significant in PCIe setting, where bandwidth is limited. In constraint, NVLink offers more bandwidth and direct connection, so the behavior difference. A common concern here is with optimizer-based system is how the overhead of this system. As shown in this figure, the overhead is negligible compared to the total fine-tuning time. More importantly, this search is one-time cost. And another common question here is, can mTuner extend beyond path to like full fine-tuning or pre-training? The challenge is that in this setting, reach update every step, making it harder to cache or reuse them due to synchronized overhead. So strategies like long-term rate caching are less appreciated. However, the underlying idea of fine-grained tensor management remains valuable, although benefits may be small and require more carefully design. To sum up with, here are the key takeaways from this work. First, even with parameter-efficient fine-tuning, we are still limited by memory and communication overhead, especially on constrained hardware. Second, our proposed abstraction, Elastic Tensor, introduced the flexibility needed to better schedule tensor lifecycle. Third, mTuner built on this abstraction to improve memory reuse. And dependence relaxed dependence relaxed communication overlap and other adaptation accumulation technique, leading to better efficiency. And finally, in package, we observed that we have up to 51.2% speed up and with small search overhead, showing that this idea are both efficient and practical. And now, thanks for your listening.